All right, well, I'm going to be talking about profiling at scale. Now, what we're going to go over is first a quick overview of why we're here and what we're talking about. We'll talk about a few of the challenges that are faced when you're scaling up your MPI programs and the difficulties in profiling and analyzing those codes. And we'll talk about the MPI Performance Snapshot tool and what it can do for you to help you analyze those codes. And where, once you're done with MPI Performance Snapshot, where you want to go next. So, what are we talking about? When you're scaling up your application, you've got tools right now that can analyze it at small scale. You get to 10, 100 ranks, no big deal. You get to 1,000 ranks, it can start getting problematic. When you're looking at tens of thousands of ranks, that gets really hard to start profiling what your code is actually doing at that point. And if a bottleneck starts to show up there, well, what are you going to do? You've got to find it somehow, but if it doesn't show up until you're at scale, you really don't have a good place to start looking. So we've come up with a tool called the MPI Performance Snapshot, and this tool is intended to help with the challenge of analyzing those applications as you're scaling up. We'll help you find where your performance bottlenecks are and what you should do next after we've gotten there. And after I'm done with that, we'll do a little bit of a deeper dive, show you how you would do that with some of our other performance tools, the Intel Trace Analyzer and Collector, and Intel vTune Amplifier XE. So, talking about the challenges with scaling an MPI code. Now, as you're trying to get up to Exascale and beyond, there's a set of three things that are contributing to all of that growth. You've got your clusters. As you grow in size, you get more resources available for your programs, so your applications are going to grow. You're going to get applications that can scale higher. You're going to get bigger problem sizes so that all of these, they're all going to feed into each other, and they're all going to grow. Now, as those applications are growing, traditional performance tools, they're going to kind of cap out. You really can't go to the high scale with these. And that's why we need a scalable tool that's going to track along with that growth so that you can keep profiling. And hence the MPI Performance Snapshot. This tool is a new tool. We've recently introduced it. It's part of the Intel Trace Analyzer and Collector. This will let you profile your MPI codes in a lightweight manner. You'll get some high-level statistics and an overview of how your application is balanced. We've tested this scales well up to 37,000 ranks. We haven't been able to test it higher yet, but theoretically, we expect it can go on the order of 100,000 ranks at this time, and we're trying to increase that. This is going to give you an application imbalance. One of the things it can give you is an imbalance between your MPI, your OpenMP, and your serial code, and imbalances within each of those. You may have a lot of OpenMP time, but if all of that OpenMP time is efficient work, you're doing good. You don't want to go and do additional OpenMP work, or at least not in those sections. You want to work somewhere else. But if you've got half of your time is OpenMP, and 90% of that half of your time is imbalance in OpenMP, you really do want to be working there instead. We're going to also take some hardware counters, and these can come out of either PAPI or out of vTune at this time. Whichever one you have on your system, you can use either. This lets you, the tool overall will let you separate the statistical analysis from the event analysis. As I mentioned, you're going to get a high-level overview. This is not intended for a tool for finding the exact problem. This is intended to show you where are you being bottlenecked. You're going to see as you scale up, you can run MPS on your code and see still scaling, oh, here's my bottleneck. And yes?
Can we ask questions in the middle, or you want us to wait?
Absolutely, I'll take questions anytime.
You said you only scaled up to 37,000, right? Is that because of you didn't have a cluster larger than that, or something?
Resource availability. That is what we have tested it up to thus far.
Okay, so if I have more cores and I wanted to work with you, would you be willing to test it?
Yes.
Okay.
Absolutely, and we'll get that set up, but we would absolutely love to be able to test on larger scales. We expect that it will be able to go to the order of 100,000 ranks, but we haven't tested it there, so if you've got resources that we can use to test that, we will be glad to set up something such that we can utilize that and make sure it's working. All right, now, as I was mentioning, you can get your performance. You can see how it's scaling. Is it staying scaling up, or is something bottlenecking as you start to scale? We're also going to, once we've gotten this data, we're going to give you some recommendations on what you need to work on next. If your problems are on the MPI side, we're going to tell you, go use a tool like Trace Analyzer and Collector and find what your MPI problems are. If it's somewhere in your serial or if it's somewhere in your computational code, either go use vTune and try to find what's keeping the parallel from working as well, or the serial, or try to maybe use Advisor to get more of that serial code into parallel code. And quick comparison of our current MPI tools. This shows about where each of them has their benefits. When you're still working on the smaller scale, Trace Analyzer and Collector is going to give you a lot more detail on it. So you can find the root of those MPI problems easier. But when you need something at the higher scale, Trace Analyzer and Collector, it just doesn't hold up very well. The results take so long to load and so long to process, it's not an efficient tool at higher scales. You go to the Performance Snapshot. Now you're going to get a lot less data out of this. We're not instrumenting every MPI call anymore. We are now getting just the statistics and just some basic hardware counters to give you the basic information. Now, one thing to point out here is you can see that this is using the Intel MPI library statistics, and the OpenMP we're pulling from the notifications built in with the Intel compiler OpenMP runtime. So to get that information, you will need to be using our MPI library and our compiler to get the full benefit of this. And I've talked a lot about this already. These are the events we use to collect, they're the events we collect. Yes?
Just one question. So for the MPS, you're using a different tracing mechanism than the iChapter.
What was that?
So when you collect your experiment data, you're using a different mechanism.
Yes, that is correct. The trace collector, the way it collects data is it intercepts all of your MPI calls and logs the message side, logs details about that particular MPI call. The performance snapshot, that's just using the basic statistics that are built into the library itself, such as how many times was a function called, how much data was sent, but we're not keeping track of when those calls happened, certainly not in relation to each other. We're not keeping a record of, okay, this message was this size. We're just aggregating how much data was sent in total.
So basically that's why it depends on the Intel MPI.
Yes. Yes, because it's using the statistics we've built into the library.
You mentioned yesterday that'll work with OpenMPI or MPitch.
Not MPS. That was a different tool. That was the vTune, which I will discuss that towards the end of this. But that was vTune, not MPS. Okay, on the left you can see some of the different metrics we're looking at. As I said, this is a very high level. You get how much time is spent in MPI, how much time is spent in non-MPI, how much time is spent in each of your MPI functions, how much data you're sending. You'll get to see which ranks are doing what, so if you've got an imbalance among your ranks, you can see that. We're going to get similar data for OpenMP. How much of your time is in OpenMP in each rank? How well does that balance? Now, as I mentioned, this is your starting point for analysis when you're scaling up. This tells you where you want to go next. This is also a fairly easy to use tool, so you can, even a novice developer can sit down and get something useful out of it to kind of get a feel of where they want to go with that analysis next. At the moment, this is only on Linux, and you have to use it via command line only. We are looking to expand that as demand and resources work for that. So, yes?
One question, if you have one-sided MPI, is that supported as well? MPI could get
What was that?
one-sided communication in MPI?
Yes, I believe the one-sided communications are currently supported by MPS.
So how do you get the transfer rate from MPI?
I don't know if, I would have to check the statistics. I have not tested it myself on a one-sided program, so I don't know what that output's going to look like. But it's going to whatever statistics we already have, that's what we're going to base it off of. I don't have one handy to try out and see what that looks like for myself, though. All right, so how do you use MPS? Fairly simple. You start off, like most of our tools, you source the environment variable script. Now, one of the things about MPS vars.sh is when you load ITAC vars, we're going to load MPS vars as well. So you'll get both of them in one shot. The only run difference is you add a -MPS into your MPI run flags, and then you run it with your two stats files that are generated. Then you get your results. Now, when you load up MPS vars, there are a few options, and these are going to tell you, or tell MPS, how do you want to collect hardware events, how do you want to collect OpenMP, and how do you want to collect MPI statistics. And if you aren't interested in a particular one of these, you can disable it, you can choose which hardware collector you want to use. You do that at the time you source your environment variables. So what does the MPS output look like? When you run it, we're going to tack on some extra information. First, we're going to generate the stats, or we'll also generate the two statistics files. And if you run a vtune, we're going to generate a set of vtune results that were for that collection. But we're going to start off with a quick summary, and that's going to show you some statistics about your time, your memory usage, your MPI balance. After you've gotten this base data, though, you've got several different things you can do. Our two default options are the summary information, which is basically what you saw with a little bit more, which I'll show in a few moments. Or you can generate an HTML report of that summary information, and I'll show you what that looks like in a few minutes. You can also get your counters and memory usage. You can get breakdowns of your MPI functions across all of your ranks. You can get data transfers per rank, per function. There are several different ways you can break this down. There are also some detailed options that will let you configure what you're going to see. Again, this is still all based off of the statistics we've collected, all a command line output, except for the HTML summary. So if we want to look at memory and counters, your hardware counters, we're just counting your floating point instructions. And for your memory usage, we'll give you averages, minimum, and maximum. For your imbalances, we're going to show you the imbalance time is what we define as, or we define that as time spent not being productive. So if you've got an MPI call just sitting around waiting for something, if you've got an OpenMP synchronization, those are going to show up as imbalance. But you can see how that balances across your ranks, what the best and the worst were, and this will give you an idea of what you want to be doing next. Now, I mentioned the HTML report. There are two components to that. A bit hard to see here, but I'll show you, in a few minutes, I'll show you one live, and we'll be able to explore that in a little more detail. What you've got here is a graph of your times in MPI, OpenMP, and serial code, and then a breakdown of, let's see, here we go, a breakdown of what each one is going to show you for, we'll just go into this in more detail. It's kind of hard to see right now, but you'll see where each one is, how much time is spent in your overall of each of those, and the imbalance in them. And then if you click on the icon on the right, that's going to take you to the counters, and you'll see your floating point, your memory usage, anything else we've captured. It's going to look a little bit different in the current version. So let's go ahead and take a look at what that looks like. Now I have to give this just a moment. I am accessing this system remotely. But we're going to go ahead and run one of our sample codes under MPS so you can see what the output actually looks like. Nope, don't want to disconnect. I want to go full screen. And you can see up above what it looked like before, but we'll go ahead, run the program. We're going to get the program's output. It's going to run. This is a hybrid code with MPI and OpenMP. And this is going to run for a few seconds. It's a simulation of electrical signals propagating through the heart, if you're interested in what you're seeing. And then what we get is, this is the summary information. We'll go up just a little bit to the top of that. All right, everything above the general statistics is the program's output. So we can see the total time, how much time did we spend across all of our, summed up across all of our ranks, how well that's balanced. We can see our hardware counters, we can see our disk usage. This program reads a data file from disk and then runs off of that. It does not write anything, so, well, it writes a little bit. That's not major to the program, though. Then we can see our hardware counters, we can see our memory usage, the imbalance across this one. Now this code is imbalanced in terms of there's one rank that's doing the visualization, and then all the other ranks are doing the actual work. So this code is naturally going to have some imbalance. And we can see the imbalance there is a fairly significant portion of time for the 16 seconds of runtime, but in the percentage, it's only about 3% total, so not too bad. Our OpenMP is pretty imbalanced because there's a lot of wait time within this particular code waiting for other things to get done. Okay, now let's go ahead. I'm going to load up or bring up. This is what the HTML report looks like. So you're going to get your wall clock time, and then you can see how much time you've spent in MPI, how much of your time is spent in computation, and your OpenMP and your OpenMP imbalance time. And if we scroll down here, we can see those same breakdowns, and here's where we're going to get our recommendations. So we're saying for this application, we got a fairly high amount of time in MPI, so we're communication bound. Let's look at improving that MPI. The imbalance, not very well balanced among the ranks. It's a significant enough percentage that it's worth looking into. If we tried to scale this up higher, then we're going to get some worse numbers. Computation time, we see we're reasonable on our computation time. We've got a good bit of time in OpenMP, but a significant portion of that OpenMP time is in the imbalance because we've got a lot of OpenMP synchronizations going on. So maybe we want to look into how could we improve that. And there's pretty much no serial time in this code, so that's 0. Any questions before I move on? Okay. Yes.
The OpenMP profiling, you said that was bound to the OpenMP or the Intel compiler, so presumably you're not using the OMPT specification for doing profiling?
I believe it was ITT Notify that we used for that. I am not.
We don't use OMPT.
Okay.
We have IT implementation.
Okay. Yes.
What threading levels do you support?
What was that?
What threading levels does the tool support?
I believe it supports any threading level.
You guys have multiple?
Oh, for the MPI threads, yes. That's supported. That's part of the Intel MPI library. That support comes from the MPI itself, not from Performance Snapshot. But we're going to detect if, let's say you are doing a thread multiple and you've got MPI calls inside of your threaded regions, we're going to pick that up when the statistics are written out for those. So MPS doesn't have to support it as such. It's supported from the Intel MPI library, and the way we get the statistics, if MPI supports it, MPS supports it. All right, yes?
There was a list of different options. Do you use those options when you generate the report or when you collect it?
These options, let me go back, is it this set of options? This is what you would use on the command line when you're analyzing it. So let's, for instance, we'll use -T, and I'll show you what that looks like. So what I'm doing is I'm running the functions report, or the MPI time report, and what we're going to get is how much MPI time was spent in each rank. These reports are only on the command line. The HTML report is an HTML5 version of the summary report.
And another question. If you have both RP and VTune, which one do you recommend?
But which in VTune? Pappy and VTune? I don't have a specific recommendation there because I have not compared the two enough. I would go with VTune because that's what I'm more familiar with. All right, so we've been talking about VTune. That's one of the topics in the, once you've done MPS, where do you go next? If we want to stick on VTune, we'll get to that in a moment. First one in my slides is Trace Analyzer and Collector. If you find that you've got a lot of time spent in MPI, Trace Analyzer and Collector is where you want to go next. This will show you some details of where your ranks are sitting around waiting, where you could improve your communication patterns to try to get a more efficient MPI usage. And if you end up needing to go to VTune, one of the things we've put into ITAC is a way to generate the command line to run VTune within an MPI program, so that you can select which ranks you want to run on if you don't want to run on the whole job. But one of the recent improvements in VTune is now you can run on a full MPI job, and what you're going to see is rather than one result per rank, you're going to get one result file per node with all of the ranks on that node put into it, even when you're using the event-based sampling driver. So no more issues with you can only run one VTune rank per node. We've solved that. It works now. So I'll go ahead and show you a bit of what that looks like. I've got a trace collected from the program, same program I was just showing you. And what Trace Analyzer and Collector is going to show you is on each rank, you can see what that rank is doing at any given time. Now there's a lot going on here, so we'll go ahead and zoom in to something more meaningful than the full run. And we can see there's something going on right here. Rank 0 got stuck in something here, and everybody else got hung up on that wait all. So maybe we want to investigate, ITAC shows us with all of that waiting, maybe we want to investigate why rank 0 got hung up in that particular location. That sort of analysis is going to go into VTune. But I want to show a few other bits of ITAC before I hop over to VTune. We've got a performance assistant over here. And what this is going to show you is some common MPI problems that we've experienced from customers. It's going to give you what that problem is. I'll make this a little bigger so you can see it better. It's going to give you what this problem is. An early reduce is you got to that reduction early. In this case, we hit those wait alls really early. You can see which ranks are most affected by it. And in this case, rank 8, actually this is from rank 8, which is our visualization rank, so it's spending a lot of time in a reduction. And I could show you the source locations, but I can't show you the source for this code, so this is blank on this one. Once you're ready to go into vTune, this is what it looks like now. You've got all of your ranks on a single node are put into one result file. You can go into your standard views and see by rank, or if you want to break it down by function. Then, let's see, do I have the one I want? No, I'll just make the one I want. So let's say we want to see a function balance across the ranks. We'll just reorder this real quick. And then now I can see, okay, I spent a lot of time in my math library, and I can see the ranks were all equal in that, or approximately equal. So I can use vTune then to investigate what each rank is doing and compare the balance across them. Yes?
Please apply looping process/OpenMP region/function.
Process OpenMP region function. Give me a moment.
No, you can just use the predefined looping from the box.
Which one?
Yeah. There is like process/OpenMP region.
Ah, there it is.
And you can, for example, you can sort it by MPI communication scheme that means imbalance actually in descending order.
Mm-hmm.
Different order. And yeah, one more time. Yeah. And on the top you will have the MPI processes that is in the critical path of execution. And if you expand the row, then you will have the OpenMP regions. And you will have if you expand the first column, OpenMP potential gain. First column, expand it using the top level. So you will have the classification of OpenMP efficiencies that you have, and you can see that there is imbalance there in this particular region. In this way. And you can either, for example, change scheduling or do something else to eliminate the imbalance.
Mm-hmm.
So how did the OpenMP come up now? Sorry, I missed that part. I thought you were looking at the imbalance for MPI.
It was sorted by the MPI imbalance, and then you expand the column for OpenMP. In vTune, some of the columns have additional detail columns underneath them.
They just swapped between the two tools, or they're not integrated. It's two different tools.
They are, at this point, two different tools. The only swapping between them is I have them both open right now.
Actually, this region contains several OpenMP sharing constructs.
Mm-hmm.
And if you apply looping process OpenMP region, and then process OpenMP region, and then OpenMP barrier segment. Then you can expand the first, right? And then expand the region. You will have the statistics by the barriers inside the region, because region can contain like several sharing constructs.
Mm-hmm.
And here you can see, for example, the most imbalanced barrier.
So which barrier you want to be focusing on. Mm-hmm. Okay. Well, that just about wraps up my slides. So if you have more questions, you want to see more on the demos, if Dimitri, you want to talk some more about it.
MPI Performance Snapshot, is that also available for the KNL? And what OS do you support?
I don't know if it's running on KNL at this time. We collect the, it is running on KNL? Okay. then yes, MPS is currently running on KNL. As far as operating system, all of our standard Linux supported operating systems.
So currently I have license for the Cluster Studio and, so how do I get?
This is part of that.
So I have
Your Cluster Edition license is going to give you access to Trace Analyzer and Collector, and MPS is part of Trace Analyzer and Collector. So if you have a Cluster Edition license, you've already got it.
No, we don't have it, so we have to, I think, get the 16.
Yes. Okay.
Also, one of the things that my users constantly complain about is scaling of YouTube. They have to run it. That's what I've been told on single, if they have,
Get 2016 Update 1, it fixes that.
And what's this, how much does it scale up to?
I have not tested. Dimitri?
Right now, we have, when you run each of the application, you will have the, result directory still node.
Yeah.
For example, if you have 1,000 nodes, you will have 1,000 result directories. And it will be challenging, to decide what result directory, what node you should remove. That's why we have MPS.
Yeah, but see,
Inside one node, I think we are pretty okay, even for KNL. So, yeah, it might analyze results a bit slower, but
makes it
it's pretty
a lot tedious. You run MPS and then you find the ranks and then so it's kind of.
Now, we do have a capability in MPI that, and I'm probably going to mess this syntax up because I don't use it often enough to have memorized it. But what you can do is use the gtool capability to only run a tool on specific ranks. So let's say I've run my program under MPS and I see, not likely, but let's say I see rank 2 is causing me trouble. So if I were to do this, well, I'm not putting the rest of the arguments because I'm not going to run this right now. But what this would do is run vtune only on rank 2. We're taking this section, where's my mouse? And we're going to prepend this onto rank 2. So I can run vtune only on rank 2. If I want to specify a different set of ranks, I can do that. If I want to specify the main reason we implemented this was due to the previous limitation of vtune of only 1 per node. So if I have a different tool that needs to run only on 1 per node, then if I add the equals exclusive modifier into there, it runs on every rank with a limitation of 1 rank per node. So that lets me pick and choose more easily where I'm going to run vtune. And if you go into ITAC, you have the capability to generate this full command line automatically. Any further questions, discussion? Yes?
What's our overhead do you incur when running this? Is there any way of quantifying that?
I don't have the exact overhead numbers, but from my experience with it, it's very small because we're using the library, or we're using the statistics collection that's already built into the libraries. We're using data collection tools that, other than the event counters, are already built into the libraries and the runtimes. So there's not much extra to add into it. We're not intercepting any additional calls. When you have the event counters in, you're going to have a little bit extra from those as well, but we're talking a small overhead. Yes?
What's the largest number of ranks you can run on this tool?
This has been tested to 37,000 ranks, and we estimate it can go to the order of 100,000, but we have not been able to test it that high yet. Okay, I'll leave this up. If there's any further questions or discussion, I can certainly take that now. We've got time. Yes?
Do you plan to have this, so that person could run a GUI and submit jobs from within the GUI interface?
No, we don't have that at this time. And I think part of that is going to be we're trying to interface with lots of different job schedulers, and we're not trying to write our own job scheduler right now. So if you're talking submit a job for this, no, we're not. That's not something we're doing at this time. I can't speak to future on that. But as far as building your MPI command line, normally we don't have a GUI tool for that. But as far as what you do with MPS, you do your same command line as normal, you just add -MPS to your argument. So not a huge change there.
How many of you folks today use the Intel MPI tools? Show of hands. And trace analyzer collector? Yeah, show of hands. What are some of the other tools that you folks use to do your analysis, your MPI analysis? Don't be shy. Nothing?
We won't bite. Don't worry.
Curious. No, any other tools. I'm curious. You know, so I guess I'd like to just ask, you use our tools. What other things would you like to see us add? Is there any deficiencies that you see that you say, wow, that'd be a wonderful feature if you could have that?
Well, IBM used to have a really nice feature, or it was an instrument that MPI library generates statistics afterwards, but I forget what the name is, I think it's still out. But it really generated nice summary statistics, or preferable to what I see from my own eyes.
Yeah. Okay. Well, MPS has moved towards that direction, up-leveling a lot of that information. Because we understand that when you go into ITAC, because it generates an overwhelming amount of information, and also, unless you really know what you're looking for, it can be overwhelming for the new user. So part of MPS, the performance snapshot, is to collect those high-level metrics. And then also we're looking for input from you as well as you use the tools. We'd love to hear from you. It's like, well, I'd like to add these things as well. We're going to basically try to control that as much as possible, because once we start doing that and adding just way many more statistics, again, it becomes overwhelming, right? So that's why when we have two separate tools, I think someone asked the question of, well, I need two separate tools. And the reason why is that there is an enormous amount of information that's being captured in both. Integrating that into one has its advantages, but also disadvantages that you have just so much more information. And with the systems getting larger, it's really, it's a very difficult problem to solve.
Well, one thing that I would have liked to have when I was working with ITAC is the ability to generate the summary statistics as a text file. You know, because I could look at it in the GUI, but I couldn't really save it anywhere as text information. It could then be processed further. Because many people want to do many experiments, and then later on kind of look through all the results that were generated for characterization purposes. And if you have a text file,
Okay.
I don't know if it's text.
James, what kind of text output on trace analyzer?
There is a command line output for Trace Analyzer. The amount I have used it is, I think I've tried it once, so I don't know exactly what it's got there, but we do have, it is documented there's some documentation in the reference manual, and if there's interest, we can look to improve that documentation on what its capabilities are.
So it seems that you're generating statistics about each individual MPI call, but I don't think there is a feature to enable you to instrument a specific function in your application. Is that correct?
What perspective are you talking about for this? Because you can instrument a singular function in different ways, depending on what you're wanting to get out of it.
So if you want to get aggregated statistics about a particular function in your application, that's an option.
Yes.
And the other situation is I want to know where my code is hung, basically, while everybody else is waiting. It just says application there. How do I get a function?
in Trace Analyzer and Collector, to see function detail, there are two ways you can do that. You can either compile your original code with -t collect using the Intel MPI or using the Intel compiler, and what that's going to do is it will instrument every function in your code, and you'll get those function entry and exits in ITAC as well. If you can instrument with the API for Trace Collector, and you can get exactly what you want in your code based on you turn it on, you turn it off, you define regions, and it's going to show up how you want it to look, or it'll show you the data you're looking for. But that's not the default of Trace Collector. Its default is we're just getting all the MPI functions.
But you don't have to do the instrumentation manually, or with trace on, trace over.
It depends on if you want everything, you just compile with tcollect and you get everything. If you want less than everything but more than MPI, you have to instrument yourself. There are ways you can do it with the Trace Collector filtering as well. We've got different levels of control available on that.
By everything, you mean terabytes of everything?
Yes. Yes. I believe, well, I'm not going to divert into that, but it is every single function call in your code, you're going to see it.
So James, do you have any more? Otherwise,
I've got one more thing I'm going to do, but you can go ahead and do yours while I get this.
yeah, so guys, again, the cards here have links to the latest 30-day evals if you haven't gotten versions of our tools to give it a try. We also have expanded our enabling programs, our free programs, if you will, around our libraries and also access to our tools. So that's been revamped as well. Links are here. If you attend the earlier Python session, if you haven't heard, we basically had a technical preview of a Python that has been optimized for the architecture as well. So, you can grab one of these cards. And see, and also, I've got books. Any other questions? I've got a few people who asked some really great questions, so I've got books here for you.
One quick question about plans.
Yes.
There was a guy in my lab who his thesis would gather up performance data and then instead of writing a terabyte out, he would combine it into equivalence classes as he collapsed it down, and then write something of a manageable size out from probably rank 0. If you look at stat and you look at its output, all it shows me is the unique calling trees in existence at that point in time. That's the kind of collapse that I would like to see for performance data. It would have shown rank 8 as an outlier, but there might have been, 1 through 7 might have all been the same, and 0 would have been a third equivalence class, something of that sort.
Okay. You said you had someone in the lab working on that?
Todd Gamblin,
I'm not,
he's participating in a bunch of sort of tool stuff. It wouldn't be that hard to find him. He's probably on travel to a conference sort of 8 out of 10 weeks, but he does answer email.
okay. I'll grab a business card for you. Sorry.
Oh, he's here.
Oh, okay.
He's one of the 8 of the 10 weeks he's traveling.
Now there was a question about the functions by rank, and this is what MPS is going to give you on that. I'm just showing rank 8 for now, just because of size on the screen limitations. I can scroll further up to see the others. Okay. If there are any more questions or discussion, I can take them now.
It's kind of nice to get a histogram of message sizes from your application. Does Snapshot do that? Grab that data out of statistics text file.
It should be in there. I just don't know off the top of my head how to get it, but give me a moment. Actually, if you want exact specific stuff, let's get any other questions out of the way, and then I'll dig into how to find exact reports after that. Yes.
G-tool will work for any tool, right?
Yes, what it does is it prepends, you give gtool, this is what I want, this is the tool command I want to run. It's going to prepend that to the application name for whichever ranks you've specified it to run on.
So you can use tcollect and collect.
Well, tcollect is a compiler option.
Yes, compile with tcollect and then run the tool on one.
If you compile with tcollect, that instrumentation is built into your code. It's going to come whenever you run it. Even if you run it with no extra collection whatsoever, that instrumentation is built into the code. It's going to write it out. So if you wanted to, for instance, do a tcollect only on a few ranks, what you would need to do is compile one version of your code with tcollect, one without, and then have a heterogeneous job where only the ranks you want run the tcollect version.